So MVS technology based on a microplate. So again, users, so the PCS, you have your glass vial. Once that vial goes into the system, you can't take it out and pipette and put it back in. It's not allowed. So there were systems where people were saying, well, I want to pipette on the liquid handler deck. I want to pipette on the bench. How do I pipette on the bench and measure it? And the PCS is not built for that. It's not, you cannot remove the vial, pipette in the vial and put it back in. So let's be clear. So Artel's one of the founders, the chief technology officer, Richard Curtis, used the PCS dye patent and made a new approach for a system that could measure volumes in microplates where the path length is variable, but it still uses 2 dyes. And here's what that system would look like on a cart. It's the multi-channel verification system. Again, a global standard platform. But now we're dealing with labware, plastic microplates, and that's a topic that we'll talk about in a little bit. So quickly, you dispense the liquids, the dyes, into the microplate. You read the plate, and you get your performance values. So a full 96 well plate is less than 3 minutes, and that includes a 1-minute shake. And the 3D4 has a 2-minute shake and about just over 2-minute read. So we can get a lot of data, a lot of volume measurements in a short amount of time. So the basic steps for the Artel MVS, we have, just like the PCS, we have a calibration step and a blank baseline step. So the calibrator plate here is run once every 10 hours or before they use the system next. The software will prompt you to run that calibrator plate. You can see there's 4 quartz cuvettes. Each one has, they almost look like the PCS cal kit, right? Cal A, B, C, D, where there's a blank one, the second from the left, the blank, and then the varying amounts of red and blue dye, the same dyes, Ponzo S and copper chloride. And there's another window to the very left. It's a non-changing neutral density glass filter. So that's the absorbance check. And again, everything that we have is on purpose. It's so that that measurement result can be traceable to international standards. And all those absorbances and all the checks are in that barcode that go onto that calibrator plate. So the baseline plate is literally a water. It's a baseline. We sell it as a bottle of liquid. It's water with preservative, and it goes into that plate to get the baseline 0 measurement. Then the customer, the user, can decide if they want to put the red dye, quote unquote, the red dye in the plate or the blue dye into the plate first. Now, why would you do one versus the other? If your methodology with your liquid handler or your pipette is always going into a dry, empty well, then you would put the red dye in first. If your pipetting methodology is going into liquid, where a small volume, say 1 microliter, 5 microliters, is being pipetted into a liquid already in a vessel, then you would put the blue dye in first, followed by the red. And we shake, and then we read, and then we get our results channel by channel, well by well, and different statistics that go along with that. So just like its sister, the PCS, it's a busy table. We have dyes for everything. We have aqueous dyes, we have some DMSO, some dyes that mimic plasma, serum, and dyes that mimic PCR, that mimic master mix. In the image on the right, you can see there's all kinds of, in the MVS world, we label them A, B, C, D, E. There's an HV, that's high volume. The one that's called out, the blue dye, is what we call the diluent. So the blank in the PCS world is the diluent in the MVS world. And then there's that call out for the baseline with no dye. What we are going to do is just make it a little easier, and we're only going to focus on the aqueous dyes in a 96 well plate, just so we can talk about some of the information and not get involved into, well, which plate type or which. So we do have a working volume that it's a software requirement. The 96 well plate says 200 microliters is your working volume. Take a look at the top volume in the chart, though, aqueous HV. We can go from 200.1 to 350 microliters. That liquid dispense, if someone wants to transfer 250 microliters, there's no diluent added and there's no shaking step as part of that methodology. So if anybody wants to measure anything over 200, there's no shaking step or diluent in that step. So 200 microliters is the working volume, and down at the bottom right, the amount of diluent required is your 200 microliters of working volume minus your target volume. So if you're 45 microliters, you're looking at 155 microliters of diluent. So again, and this was, I think, an easy concept to understand, where we can measure small volumes because we can put more dye, we can concentrate the dye into the water, essentially. So those glass vials, these are the same glass vials as the blanks, and I took them out. I wanted to use them just to show that we have diluent on the left, range A, quality A, and then E. And A is used for the higher volumes. You can see it's used from 50 microliters to 200, and E is for the lowest, 0.1 to 0.99. So again, every volume value in the range on the left, the 0.1, the 10, the 50, all are the lowest target volumes in the range, and they have the lowest absorbances of the red dye in that range. Same as the volume values in the table on the right. They have the highest target volumes in that range, and they equivalent to the highest absorbance in that range. Now, this is where we're going to get a little, I don't know, we'll have a little fun here. I took my little aliquotter pipette out the other day, and I took a couple photos, and this is where the two dyes differ for the MVS and PCS. So here's our range HV, the high volume, and I spread it out onto Kim wipe. And what you need to know is that the MVS is different because in those bottles of dye that are called red, they also contain the blue dye. And I just want to hit the pause button on that. So the PCS, you have blue dye in the vial, and you have only red dye in the bottle of amber bottle, and you're putting red dye into blue. In the MVS world, we have the blue dye diluent, and in this bottle that's amber is blue and red. And the blue dye is at the same concentration each. And this is where that works in the microplate. So when you're adding 50 microliters of range A to 150 microliters of diluent, the blue dye is not being diluted. It stays at the same concentration. If you're adding 100 microliters of sample solution into 100 microliters of diluent, the blue dye is not changing. So we use that blue dye to calculate the path length in each well. And I think I'd like to ask if there's any questions here, because we are going to come back to this, and it's going to kind of be, and that's where that microplate, the variable path lengths. So we're going to calculate 96 individual path lengths in a 96 well plate. Any questions on that? So we're going to look at it as a schematic in an absorbance window, if you will. So these Polishore amber bottled red dyes also contain the blue dye, and the red dye has different concentrations. So in the little schematic on the bottom on the left, the absorbance of the red at the lowest is going to be used for higher volumes, and as you go up a little bit higher in concentration, it's going to be used for lower volumes. So this could technically be the Polishore A in the lowest, Polishore B in the middle, and then the C in the highest. But every single one of those is noted by the absorbance of the A sub B, the absorbance of the blue, is at the same concentration of blue dye. And if we look at the diluent and look at that schematic down on the right again, the lower right, The diluent only contains blue dye, and if you it's the same relative concentration as it is in the sample solution. So again, I don't know if it's common, but in the US in the summertime, you can have a lemonade and iced tea mixture, and just think of a lemonade iced tea mixture and you're adding lemonade to it. So you're just adding blue dye to a liquid that already has blue dye in it, and now we're looking at the red. Any questions there? European audience is quiet. That's okay. So I'm going to show you some data here that it might make you flinch a little, but the diluent is most important at the smaller volumes, and there's reasons for that. But let me show you what it looks like as a measurement of measuring those red dye numbers on the side, on the left, and then remeasuring once diluent, the value on the right, is added for high volumes. So in the chart on the right with the dark blue, there's no diluent added. And then it's remeasured after that amount of diluent is added to equal the total volume value of 200 microliters per well. If you look at it's pointing to the legend, with no diluent added, it's a shorter path length, and the red dye is a stronger signal. The concentration is higher. And then when the diluent is added, it's a longer path length, right? The total volume is the depth of the liquid is the path length. And then, in these situations, the red dye is weaker. Let's make it real easy on ourselves and look at the 100 microliters way to the right. 100 microliters starting with no diluent has a short path length and a relatively higher concentration of red. When you're adding diluent at the same amount, so you're doubling the volume, you're doubling the path length, and you're cutting the red dye concentration in half, if you will. So shorter path length, higher signal, longer path length, weaker signal, same result. So why do we need diluent? If we're getting the same measurement results? This is the high volume values. So this is only in what we call the A range. It's most critical. So below 100 microliters might not cover the bottom of the well. So we needed a way to create a standard volume value that could not only help us create a reliable depth measurement of the path length, but also enough liquid in the well so it could mix efficiently. So for software, for training, for purposes of using, we stuck with 200 microliters as the total working volume, so that customers had a value to fixate on, and that's what you shoot for. The diluent is non-quantitative. So because of the blue dye value, it doesn't have to be accurate. If we want it to be close to 200, but if someone is measuring 50 microliters and they add 100 microliters of diluent, 150 total volume, you're still going to get a volume measurement value that's traceable. We just want you to be close. So the worry is that when they over pipette diluent, and there might be a 20% overage or so, because once you start getting into the 210 microliters, 220 microliters, 10% over, when you're shaking in our vigorous shaker, the liquid could potentially launch out of the well.
So what you're telling us is
perfect
that
time.
In principle, we don't need the diluent, because to me, I don't see any big difference between those bars. But it's just for ease of use, so that people get used to these 200 microliters.
I think you're correct on both, and because we're all colleagues here, at the higher end of range A, you don't need diluent. You can make the measurement. To have more uniformity as a message to customers, get your wells close to 200 microliters with using diluent for every well. Yeah, it really makes an impact, Andreas, below 100 microliters. Absolutely.
Okay.
Big, way more of an impact.